All right, the last exam, or the last section, I should say, for exam 3 is 17.1, and that's Green's theorem, which is one of the three big fundamental theorems in vector calculus. We have Green's, Stokes, and divergence. The fundamental theorem of calculus is very similar to what we have in Stokes' theorem, and really Green's theorem is a result, is a two-dimensional version of Stokes' theorem. So they're all sort of grouped together and in higher dimensions and farther in calculus and analysis, all of these theorems are actually unified. So zoomed in, they look very different, but from a far out perspective, they actually all become the same, which is pretty neat. But for the time being, let's look at 17.1. What is Green's theorem? So Green's theorem is a result that allows us to talk about relating a line integral, so an integral about some sort of one-dimensional thing, a curve, to a double integral, which is an integrating over something that's two-dimensional. So this is interesting because it goes from one dimension to two dimensions or vice versa. Because this is an equality here, in math, equalities mean they work both ways. So it's not that we're just taking line integrals, converting them to double integrals. We can also take double integrals and convert them into line integrals, provided we have enough information and things work out nicely. Just because Green's theorem applies doesn't necessarily mean Green's theorem is the best thing to use. Like all tools, tools are wonderful, but not every tool is the right tool for the job. So let's talk about Green's theorem. So Green's theorem says let D be a domain whose boundary, so you might have been a while or maybe the first time possibly that you're seeing this notation. So true, this is the same symbol that we use for like partial derivatives, definitely. We'll just say, we'll call this like, we'd read this as del D. And this symbol is used to denote the boundary of something. So we want an enclosed domain whose boundary is a simple closed curve, and we're going to orient this curve counterclockwise. So let's go ahead and just draw some amorphous blob. Okay, there's some amorphous blob. So the domain is the interior of this amorphous blob. And then the curve that I drew first that contains the shaded region, that's going to be the boundary of D, del D. We want this curve oriented counterclockwise, so like that. Using the right-hand rule, if our thumb's pointing up off the screen, or out of the screen, I guess from your perspective, or for me on my iPad, it's I'm just putting my fist on top of the iPad and my thumb's pointing up directly. I curl my fingers, and then it's that direction. Another way that we can visualize this is imagine this is a bird's eye view looking down onto something. Maybe imagine that this is actually like a pond. And you're going to walk around the pond in this direction. If you walk in this direction, your left hand would be pointing, or you can imagine holding your hand, your left hand, above the surface of the water of the pond. So some people prefer this analogy, especially when domains become more complicated when we move into, after exam 3, Stokes' theorem, when we have surfaces that are not just in the plane. This can be a useful interpretation. So we want to orient our curve so that if we walk around it, our left hand is over the surface of, or whatever that domain is, or in this case, hypothetically speaking, the surface of the water of the pond. All right. So that's the kind of setup that we have here. So this is saying if you are asked to calculate the line integral of some vector field around this, in that direction, so in this orientation, the way that I'm tracing it, you can relate that line integral to integrating over the entire area of this particular quantity. And you may notice that this particular quantity is exactly what we check to see equals 0 for checking if something's conservative. That's not a, that's not a coincidence. These two things are very much linked. Because remember, what is this right here? Well, this is a line integral over a closed path. And we know that if a vector field f is conservative and we're integrating over a closed path, then we know the result has to be 0. So that means this integral would have to be 0. Well, one way to ensure that this integral is 0, regardless of what the domain D is, we could ensure that this is 0 if this difference is 0. So these two things all link up, but what is important to know here is that Green's theorem is not a statement about conservative vector fields. Nowhere here in this page at all do we talk about conservative vector fields. In the assumptions for Green's theorem, we do not assume that f is conservative. This is just a statement about line integrals in general. So our vector field may or may not be conservative. Green's theorem, you could still use it provided that you're integrating over a simple closed curve oriented counterclockwise. Okay. So what an interesting result here is if you can find a vector field. So if you can find some vector field f1, f2, so that when you calculate this, if you just so happen to get 1, then what happens to Green's theorem? Well, in Green's theorem then, we end up getting this double integral literally becomes the double integral over d of 1 dA. And we know what the double integral over some domain 1 dA is. It's simply the area of whatever that domain D is. So you can compute the area of something by doing a line integral around the outside of that enclosed region using a vector field that has this property. Well, what are some examples of vector fields that have this property? Well, here are 3. And you can verify. For instance, let's go ahead and look at this one. Sort of a, pathological example, but it does work, right? Del f2, del x is 1. Del f1, del y is 0. 1 minus 0 is definitely 1. So this is one such vector field that would work. All right. And also, just to emphasize here a little bit more that these are not the only 3 fields that you can use. These are just some pretty simple ones. Some may, one could argue that they're the simplest examples of vector fields that have this property, since the functions themselves are just linear functions, which is the simplest thing you can have. But there is an infinite number of vector fields that have this property. Okay. So what we're going to go ahead and do here is take a look at this bullet point here, which is best elaborated with a visual. So imagine we have more complicated domain. So let's say we have something like this. So there's a hole, and maybe there is another hole, and then there's this patch in the middle. So our domain is actually, let's say, oops, don't want to connect them. So that. So this area in blue here is sort of outside. We don't want that. Okay. So that's our domain D, that red shaded region, including this area here. So be mindful of that. So if that's our domain D, then what does the boundary of D actually look like? So this is kind of strange. So the boundary of D actually would consist of a few different curves. So in particular, I will go from the outside. We have the outside curve, C1, which is this curve. So that's obvious. That's certainly a boundary. But so is this curve. So let's call that C2. Well, also this is a boundary. So that must be, well, C3. And also this is a boundary. So C4. So the boundary of D actually consists of 4 distinct, disjoint, simple closed curves. So what we're going to do now in this boundary of D, how we want to write this, well, the boundary of D is going to be the union of C1 with C2 with C3 and C4. So we just glue them or union them all together. But if we're going to think about using Green's theorem, we have to orient all of these boundary curves in a way that is not necessarily counterclockwise. So this works if it's a single thing. Counterclockwise is the right word to use. But really what we want to do here is have it be oriented positively. So if the domain D lies to the left, so this is where that analogy of interpreting this as like a body of water, like a pond, and walking around it with your left hand over it, you want to orient it in such a way so that when you walk around it in that orientation, your left hand is above it. So that's why I don't always like the term counterclockwise, because counterclockwise does depend upon your perspective. When you're looking at the screen here, this is certainly counterclockwise. But if this were some sort of like, one of those see-through mirrors that they use in interrogation rooms, if you were to, on that glass, if you were to draw a curve, then the people inside the room, the interrogation room, would see it counterclockwise. But then the people outside looking in would see it clockwise. So the term counterclockwise and clockwise are great to use when it's very clear what your orientation is. So in this case, we only had one curve, so counterclockwise makes sense. And our orientation, where we're viewing it from, makes sense because we're not pretending that we're inside the screen looking out. So down here, for this curve, counterclockwise would be the right term, because as we walk around it in this orientation, if you imagine bird's eye view, your left hand would be like that, pointing inward. So we want to go ahead and orient C1 with this orientation. C2, on the other hand, we're actually going to orient it this way, which, of course, is clockwise from our perspective. So that's why I kind of abandoned the counterclockwise and clockwise terminology at this point. Really, the better intuition is to think about walking about it in both directions and see which direction does it force you, your imaginary person walking here. Where's your left hand? Oh, it's over this region. So that's the correct orientation. Same thing here. For C3, we're going to orient it this way. And for C4, we're back to counterclockwise. So, now that we have that, that's how we want to orient our curves. So when we do our line integral, the line integral around the boundary of D, I'm not going to write all the stuff here. I'll just do dot, dot, dot. This is equal to the integral of C1 plus the integral over C2 plus the integral over C3 plus, lastly, the line integral over C4, that should say. So that's what you're going to need to do. Now, let's change gears for a second. Let's think about what happens if you orient one of the curves backwards because you forgot, or sometimes it's easier to orient something or parameterize something in one direction than it is the other direction. Some ways are more natural. So let's just think about it this way. So what happens if, let's go ahead and say that we actually parameterize C2 in this blue direction. Okay, so let's just pretend we're going to use the blue direction. So we'll keep C1 the same orientation. C2 will get mixed up. C3 will keep the same, but C4 will also mix up. Okay? So we're now just going to look at the blue orientation marks. So in this case, the boundary of D is still considered that. But what's going to end up happening here is when it comes time to take a look at our line integral and breaking it up, it's going to be different. So the line integral over the boundary of D will be we're going to go ahead and have C1 plus the line integral over C2, which is the opposite orientation, right? This is not good. It should be this way, but this is going the opposite. So if it's the opposite of what it should be, we're actually going to have a minus sign here. Plus the line integral over C3, and C3 stayed the same. It's the correct orientation. And then C4 is also opposite of what mathematically positive is. So we have that. So the changes here are, we have to incorporate those changes. So really your orientation actually doesn't matter. It's not like one orientation is inherently better than the others. What really this affects, your choice of orientation will affect how you write this decomposition. Are you using all plus signs, as we did up here? Or do you have to use some minus signs because the orientation was flipped? So some may argue that this is better because you don't have to worry about the sign. And that's true, like to a degree. But in actuality, if you're struggling to parameterize this curve in this orientation, but you know how to parameterize it in that orientation, go ahead and do it in the way you know how, and then all you do is have to pay the cost of a single negative sign there. So that's not a bad price to pay for flipping the orientation. And that is it. Good luck on exam 3.